Okay, so let us again discuss functions. We have seen the definition of a function, and we have also seen what explicitly defined and implicitly defined functions mean. So now we next proceed. Functions obey the axiom of substitution. And that means this: if x equals x prime, then fx equals fx prime. The author asks why, and this of course comes from the definition of a function, specifically the condition which says that for a given element in the domain, the output should be unique. There should be a unique element in the range to which the given element is associated by the function. So it's from that uniqueness that we are getting this. That is, equal inputs imply equal outputs. On the other hand, if we have unequal inputs, then the outputs are not necessarily unequal, don't necessarily ensure unequal outputs. As the following example shows. So we now have an example, and this is example 334. And the example is this: let this, of course, this is an example of a function. We are going to see a specific function here. So we will need a domain, a range, and a rule for assigning the elements of domain to the elements of range. So the domain is x, which we take in this case to be the set of all natural numbers. Range also we take the same set, the set of natural numbers. And for x and y belonging to n, let px comma y be the property y is equal to 7. Okay, so this is our property px comma y. So to see that this property is capable of creating a function, we have to check that for every element x in x for every element x in x, there must be exactly one element y in y. In our case, x and y are same. In general, they may not be same, such that this property is true, which in this case is clear. Clearly, for every x in x, which is nothing but a natural number, for every natural number, there exists exactly one y in y such that px comma y is true, and that y is this number, y equal to 7. So px comma y defines a function f from x to y, means from n to n, or I think it's better to write x to y, because for us both x and y are n, but this is how we generally write this. So we write it in this way: x to y, that maps every natural number x onto the natural number seven. So the remark that unequal inputs, if we have unequal input, then the outputs are not necessarily unequal. This example shows the extreme case of that, where every input has the same output. All the inputs have the same output, 7, and the inputs are all the natural numbers. Okay. So now, having seen this example, there is a remark after this. So this is remark 335. At this point, we are using parentheses to denote several different things in mathematics. On one hand, we are using them to clarify the order of operations. For instance, you compare these two calculations, say 2 times 3 plus 4, so this is 14. You compare this with 2 times 3 plus 4, which is equal to 10. So that means using parentheses, the whole thing changes. The meaning of the expression changes entirely. So this is one use of parentheses. On the other hand, we are also using parentheses to enclose the argument of a function. Argument of a function fx. For a function, the input is actually called argument. That's it. So we use parentheses to enclose that, or the argument of a property, or that of a property, for example, px. Here also you can see that to write that type of property which depends on two objects, there also we are using parentheses. Why we say these things? It's because these two uses are different. You can clearly see here the meaning is something, here it is something else. So will this cause any problem, any ambiguity? However, these two situations don't cause ambiguity because the intended meaning is clear from the context. And how is it clear? If A is a number, then A times B plus C means A, you take the product of A and B plus B and C are of course numbers. But if f is a function, then f b plus c does not mean f times b plus c. It means, you see, that's why this remark is there, because there is a possibility for confusion. So to clear that confusion, we are having this remark. Okay, this is the output of f when the input is b plus c. And this difference is clear because when you are writing this, you will know that this f is not a number but a function. In some cases, this distinction may be difficult to notice, but there will be no situation where you will get confused. Usually the context makes things clear. Okay, sometimes there is something else. Sometimes the argument of a function is denoted by subscripting instead of parentheses. Let me refill this. Okay, sometimes instead of writing the output like this, we write it slightly differently. It's the usual practice. But when For example, a sequence A0, A1, A2, etc. Sequence means infinite sequence. A sequence of natural numbers. We are taking a sequence of natural numbers because remember that that's what we have till now. We don't yet know about integers and other higher number systems. So a sequence of natural numbers is strictly speaking a function from n into n. Okay, a function from n into n. Here the output of, okay, a function, I may as well give a name to this function, because otherwise how shall I write the output? Oh, I already have written the name. Okay, how foolish of me. Is a function from n to n which maps n onto an, that is, we write the output an. See, this is what the function does to the input 0. It maps 0 onto this natural number a0, whatever it may be. That entirely depends on what how the sequence is defined. But instead of writing a0, we write that input 0 as a subscript. That's the usual practice. That's how we write a sequence. That's because you see, a sequence, when we ordinarily think of it, is an ordered list of objects. That's how we view it. So there is a 0th object, a first object, a second object, and so on. Or if you want, you can call this also the first object, second object, etc. So we write the output as an. Okay. So after this, there is another remark. This is remark 336. Strictly speaking, a function is not a set and a set is not a function. They are different types of objects. It does not make sense to ask whether an object X is an element of a function F. Also, it does not make sense to apply a set A to an input X to generate an output AX. These things are meaningless. If we are given an object X and a function F, then we cannot ask whether X is an element of F because F is not a set. Similarly, if we are given a set A and some object X, we cannot apply the set to the object to generate an output, considering the object as an input, because this is a set, not a function in general. However, if a function is given, then we can sometimes generate a set from that function known as the graph of the function. If a function is given, we can define, or we will see the definition later on, although you may already know. You may know means you already know what a graph of a function is, at least in the case where the domain and range are both the set of real numbers. We can consider the graph of the function which in general looks like this. And this we will see in section 3.5. So it's coming. This is section 3.3. In the 5th section, we will see that. Okay. Now next, there is the definition of equality of two functions. When we say two functions are equal, that thing. Just like equality of sets, there is equality of functions. And the definition is natural enough. So this is definition 337. Equality of functions. Two functions f and g having the same domain and same range. Domain is x, range is y for both of them. That has to be the case first of all. R said to be equal if for all elements in the domain we have fx is equal to gx. That is, they not only have the same domain and range, but they do precisely the same thing to every input. They generate the same output. When f and g are equal, we write f equal to g. Okay. Note that if f and g agree at some points of the domain, but not all. Agreeing means having the same value at that point. If fx is equal to gx for some x in the domain, but not for some other x, then we don't say that the functions are equal. Then f and g are not equal. However, there is a concept of, a weaker notion of equality where this is permitted. And that we will see in chapter 19, which involves limit integration. That is the last chapter actually. In chapter 19, we will come across a weaker notion of equality. Namely, two functions being equal almost everywhere. Almost everywhere means the set of points where the functions are not equal is a set of measure 0. What is the measure of a set? We will see those things later on. Okay. Equal almost everywhere. And equality has anything not been written about that? Equality of functions satisfies the usual properties. That is, it is reflexive, symmetric, transitive, and it satisfies the substitution axiom. Those things are there. But before that, there is an example. So this is example 338. Oh, and I must mention that this is informal because it uses things which we have not developed yet. Now functions x being mapped to x square plus 2x plus 1 and x being mapped to x plus 1 whole square are equal on the set of real numbers. They are basically the same thing. The functions x mapped onto x and x mapped onto absolute value of x are equal on the positive real axis. You see, there are many undefined terms here. we are not saying what R is, or I mean we are saying but we don't yet know, we take that view. We are also using the absolute value function which we have not defined properly. So that's why this is informal, and you have to understand these things. See, positive real axis. What is positive real axis? You have to understand these things in terms of the prior knowledge that we have about them. Okay, positive real axis, but are not equal on R. So equality of functions depends on the choice of domain. Sometimes if the domain is properly restricted, then the functions turn out to be equal. But if it's too large, they may not be equal. So it depends on the domain. Okay, then this example is something of a triviality, but nonetheless it's important. Should I use the words boring and those things that Tao has used? Okay. There is a rather boring example of a function for any set x. There exists a function f from the empty set into x. Known as the empty function. Although it may be boring because it has no use, not very good use, but nevertheless it's still somewhat strange, known as the empty function. Okay, what is the definition of this? You see, when we define a function with say domain x and range y, we need to say what the function is doing to the elements in the domain. That is, to what elements, suppose this is x, this is your y. Now there are elements in the domain. We have to precisely say the outputs for each input in the domain. Okay, what the function is doing to these elements in the domain, how the output is being generated, that we have to say. Otherwise the function has not been specified fully. Here, however, in this curious case, let us first see what it means. You see, if we write the condition for a function, condition for a relation like this to be a function, what is it that we have? If x belongs to x, then there exists a unique y belonging to y such that px comma y is true, where p is the property that is defining the function, and the property itself has that same condition, that is, for every x in x there is exactly one y in y for which this property is true. Okay, Now we can write this whole thing, this is an implication after all, right? In that fashion also we can write x belongs to x implies there exists a unique y belonging to y such that px comma y is true. Okay, now if I apply this condition of a function on this particular case, then what do I have? You see here the domain is empty set. So that means for every x belonging to the empty set, I have this. Where of course for this y has to be, okay, let me just write it once more for the sake of clarity. A unique y belonging to x, don't confuse this x with this x, okay. Here the range is x such that px comma y is true. But what is this p? If we don't mention what p is, then of course how am I getting the function? But you look at this implication. In this implication, this part is the hypothesis and this part is the conclusion. What about the hypothesis? Is the hypothesis true? No, it is never true. For every object x, whatsoever